Okay, students. Now let's talk about something different. Now that we know the rocket equation, you just need to know whether single stage or multi stage is more beneficial. So we have this rocket equation delta V is equal to ISPGE ln MO by MB, where MO is the original weight or original mass. Sorry, it's not the weight, it's mass. MO is the original mass. It consists of the structural mass, the propellant mass, and the payload mass. Whereas MB, the denominator, consists of the structural mass and the payload. Now, how can we increase this velocity increment, delta V? From the equation, you get the idea. MO is actually the total mass of the rocket. So if you increase this MO by increasing the propellant mass, you will get more delta V. That is mere common sense, or very, you increase the propellant mass, you deliver more power. So the delta V should increase. That's one way of thinking about it. The other way of thinking is you have freezed your total mass. Your propellant mass is fixed, your payload mass is fixed, and you have only left with playing the structural mass. Now look at this denominator. If by some means we can bring up with some ingenious material or any sort of design by which you can decrease this MP. Okay, you decrease the MP, you decrease the denominator, delta V increases. Okay, so what does MP consist of? It consists of the structural weight and the payload mass. So obviously if you reduce the payload mass, you'll get more delta V because the mass is less. But if you are freezed with the payload mass, only one option, you have to reduce the structural mass. Now how do you reduce the structural mass? Let's say for example, you're just igniting a rocket. Okay, so this is your what do you call payload, the red color tip of the rocket. You have the payload mass, and this is the propellant filled in, and you have the structural mass, and you're lighting up igniting this rocket, and it goes all the way up here. Okay, when you reach here, you can notice that the propellant mass is completely burned out. Okay, now all left is the payload mass and the structural mass. Now look at here. If you calculate the delta V at this point, delta V is equal to ISPG. Now this is actually can be rewritten as Vj also. Okay, just to remind you, this can be also written as Vj. So I ln MO, which was weight of the rocket, the starting point, divided by MB, which is the weight of the rocket right now. Now imagine if you can shell off, or just during the progressive movement of the rocket, if by some means you can just get rid of some of the structural weight, which is not useful. Okay, because once the propellant has burned up to this point, there is no need of this much portion. Okay, just if you can just get rid of those portion, your delta V at that time instant increases, because when you calculate MP is much more less. Okay, it doesn't consist of the whole thing, it only consists of the mass up to this point. Okay, so that's mere common sense. So in a way you can say that if you want to increase the delta V, you can play with the structural mass. So by any means, if you can just get rid of the structural mass as you go from point A to point B, okay, that increases your delta V. And for that reason, so say suppose your rocket is starting from this point. Okay, now you have this much propellant. As it reaches here, let's say it completed its first stage, and it has get rid of this portion. Just get rid of this portion, it goes down. So your structural mass has decreased at that point. So this is the logic actually. So multi-staging is much more beneficial than single staging if your intention is to increase the velocity increment, and that actually gives you a very good thing, because if you increase the delta V, what does it mean? You can actually increase your payload weight. See, your payload, you can deliver a high payload mass, larger mass of payload to the orbit. That is what it implies. Okay, so how do you increase the delta V? You decrease the structural weight, or you just get rid of the structural weight as the rocket progresses from one point, from uh, the ground to the orbit. All right. So to give you a very good understanding, I'll work out a question, work out a problem, and that will give you much more clear understanding. Before going into that, I just want to clarify one thing. It's I talk when I whenever I talk to you, I just said mass, not weight. Okay, if I for any reason I mentioned weight, that is wrong. Beg your pardon. It should be mass. Okay, structural mass. You have to reduce the structural mass, not weight. Now, why I'm saying this, I'll give you I'll give you understanding. I need to focus your attention here. What is actually weight? Weight is mass into acceleration due to gravity. Now, what is this acceleration due to gravity? It's a constant 9.81. Now, how do you calculate this 9.81? So from Newton's law, gravitational force, you have force is equal to gravitational constant g into the bigger mass into the small mass divided by the distance between those mass square. Okay, so that's how you calculate the gravitational force. So the gravitational constant happens to be 6.67 in 10 raised to minus 11. So that's the reason why if you have a very small mass, because of this constant, the amount of gravitational force is very less. Okay, whereas if you take two masses which are at a very large distance, okay, distance apart, and if you have a huge mass, if you have a huge mass, then this constant, that cancels out this 10 raised to minus 11, and this becomes a predominant value. We'll see that. So the gravitational constant is this. Mass of Earth is 5.972 into 10 raised to 24, and this is our smaller mass m, okay, or our satellite mass, divided by the distance between the rocket, and not the satellite mass, the rocket mass, uh, distance between the rocket and the center of the Earth. Okay, so the radius of the Earth happens to be 6,378 kilometers. So into 10 raised to 3, convert that to meters square. Okay, so if you calculate this, you'll get 9.8 into this rocket mass. So if you calculate the weight of the rocket at the surface of the Earth, this is the formula that you use. Okay, the mass of the rocket into 9.8. Okay, now suppose that this rocket has reached 800 kilometers above the Earth. Okay, so that is somewhere near the low Earth orbit. Okay, below 1200 kilometers, you can think of any orbit below 1200 is considered to be a low Earth orbit. So 800 kilometers above the Earth. So if we calculate the acceleration due to gravity at 800 kilometers above the Earth, now the distance between the rocket and the Earth center has increased, right? It's the radius plus this 800. So 6378 plus 800 is 7778 kilometers, 7178 kilometers. So if you plug in this value and calculate, the acceleration due to gravity is 7.73. It has reduced from 9.8. So that's why I'm always mentioning about the mass, not the weight. Okay, the weight always depends on the position of the rocket from the center of the Earth, and that is true for any bodies when you calculate the gravitational force. Okay, so that is why mass is important, not the weight. Okay, so let's do the problem. Okay, problem is very simple. You have to deliver a payload of 1000 kg. The initial mass of the rocket is 15,000 kilogram. The structural mass is 3000 kilogram, and the exhaust velocity is given as 3000 meter per second. So this is somewhat your rocket. Let's say your payload mass is 1000 kg. The structural mass, the structure of this rocket is, the mass of the rocket is, structural mass of the rocket is 3000. The total mass, including the propellant mass plus structural mass plus payload mass, is 15,000. So you have to calculate the delta V, considering it as a single stage. and then you have to calculate the same delta V considering it as multi-stage or two-stage. So in two-stage you can assume that both the stages are identical. What does that mean? Identical means your delta V1 is equal to the delta V2. The delta V created in the first stage is equal to the delta V created in the second stage. Okay, so the first stage, if you can consider it as a single stage, you have the rocket equation delta V is equal to Vj. ISPG is nothing but Vj, ln mo by mb. So Vj, your exhaust velocity is 3000, total mass is 15,000 by the burned out mass. Structural mass is 3000, the payload mass is 1000. So the total mass after the propellant has completely burned out is 3000 plus 1000, 4000, 15,000 by 4000 gives you 3965. So this is for a single stage. So the second case is two stage. So the assumption is you have identical stages, which means delta V1 is equal to delta V2. So the point to be noted is that that may not be true all the time. Okay, so in this case, if you assume that it is identical stage or the single stage, the delta V1 created in the first stage is equal to the delta V created in the second stage, then you can think of then that implies that the lambda 1 is equal to lambda 2. What is lambda? That is the payload mass fraction, and epsilon 1 is also equal to epsilon 2. That is nothing but the structural mass fraction. So this is your two stage. So how do you calculate the individual stages? In this, the important thing you have to note is that this is your first stage. Okay, after the first stage, this much portion is discarded. So what is this? What is a payload when you consider the first stage? So first stage, the payload is actually the mass of the rocket up to this point, or the second stage, the complete mass in the second stage. That is your payload in the first stage. So that is a point you have to note. Or if m naught 1 represents the whole of the mass of the first stage, and m naught 2 represents the whole of the mass of the rocket in the second stage, after this portion is discarded, the payload for the first stage is considered to be m02, or the total mass of the rocket in the second stage. So that is what you have to deliver after the first stage. The payload that you have to deliver is this. So m02 happens to be your payload. Okay, that is a point you have to know. Now what is the payload of the second stage? ml, your usual payload that is given in the question. So if you consider identical stages, the equation is very simple. Okay, all you have to do is, since delta V is equal in the first stage and second stage, just total delta V is nothing but delta V1 plus delta V2. Okay, so 2 into, you calculate the lambda and epsilon. So this is your formula, 2 into Vj ln 1 plus lambda divided by epsilon plus lambda. Now the question is, how do we find out the mass fractions? So basically you have the first mass fraction, payload mass fraction. Payload mass fraction is given as payload mass divided by the structural mass plus propellant mass. Okay, payload mass is, in the case of first stage, the payload mass is what? The whole of the second stage mass. Okay, m02 divided by structural mass plus propellant mass. Now that can be also written as, if you could remember. So if you could remember, what is MO? MS plus MP plus ML, or the structural mass plus propellant mass plus payload mass. And if you calculate the mass fraction, payload mass fraction is the payload mass divided by the structural mass plus the propellant mass. That's our formula. Now this can be also written as ml whole divided by mo minus ml. That is nothing but ms plus mp. Okay, mo minus ml. Okay, that is ms plus mp. So we're going to use this one. So here, if you look at this, This is what you get. MO2 is our payload right now, divided by the total mass minus the payload M02. So that is how you get this formula. Okay, when you calculate lambda 1. Lambda 2, in lambda 2 you have the stage at this one. So here the payload is ml, the total mass is M02. So ml, the payload mass, divided by the total mass minus the payload mass. Okay, so if you have a lambda 1 is equal to lambda 2, equate that, you will get m02 is equal to root of ml into m01, and you simplify that, you will get 3872 kg as m02. You plug in that value here in lambda 1 or lambda 2, you'll get the lambda 1 as 0.348. Okay, so that is the same as lambda 2. Now similarly, if you consider the structural mass fraction, structural mass is nothing but, what is structural mass is mass fraction? ms divided by ms plus mp, or the structural mass divided by the structural mass plus propellant mass. So here for payload mass and structural mass fraction, the denominator is the same, so you can always write this as m0 minus ml. Okay, or the denominator is same for both cases. So your structural mass ms1, you don't know actually what is ms1. What I've done is the question, sorry. So in the question, the structural mass, total structural mass is 3000. Now if you divide that into two stages, the total structural mass should be 3000. So you can say that ms1 plus ms2 is 3000, and we are considering the first stage. So ms1 divided by the first stage denominator is mo1 minus mo2. See, your first stage, your payload is mo2, your total mass is m01, so m01 minus m02. And your second stage, the payload is ml. We are supposing that the mass fraction, the structural mass mass is ms2. So ms2 divided by second stage, your total mass is m02 and your payload is ml. So m02 minus ml. So when you calculate the mass fractions, the payload mass fraction and structural mass fraction, you can get into this form. That is more handy. So equating, you will get to this form. You simplify, you get epsilon as 0.214. Then you have, once you have lambda and epsilon, you just plug in the values, you will get the answer as delta V is equal to 5249.25 meter per second. If you compare this value with the first value, 3965, see this one is 5249. So delta V is definitely larger for multi-stages. Okay, so what is actually multi-stage? Multi-stage is something like sequentially arranging the rockets so that after each stage, the structural mass of that stages can be discarded, or a portion of the structural mass can be discarded after each stages. Okay, so it is like sequentially arranging the rocket, number of rockets into one single rocket. Okay, so from this question, it is very clear multi-stage is more efficient, or multi-stage gives you a greater velocity increment, or delta V, compared to single stage. Moreover, the important thing you have to note is that single stage, let's say suppose you have to deliver the rocket somewhere at geosynchronous orbit or something like that, very large distance, not just 800 kilometers or 1000 kilometers, something like 32,000 kilometers or something like that. So at that far away point, if you want to deliver the satellite at one go, if you are using a single stage rocket, the mass of propellant that has to be stored is very huge. Okay, so the idea is you have to get the rocket at one go to the orbit, which is 32,000 kilometers above the Earth's surface. So you have to store a large amount of propellant. The propellant mass is going to be very, very high. So if the propellant mass is going to be very very high, your structural mass is again going to be high. Okay, so there is no benefit in in actually using more propellant. The benefit lies is in actually using less structural weight or discarding the structural weight in sequential or as the rocket progresses along the trajectory. So that is the best way possible. And so that way, multi-staging or single staging cannot be used for getting the satellites to very very high orbits. Multi-staging is the only way by which you can achieve that. Okay, so that completes our single stage or multi-stage comparison, and we have also seen the rocket equation.